Hey guys, this is going to be a review over the Unit 1 Limit and Continuity review on the AP Classroom website. I'm not sure what kind of details they give you once you submit it, if it gives you the full breakdown on how to solve it. Regardless, I'm going to go through on how to solve all of these questions. The actual test will be very similar to this, exact same format, very similar questions. So if you understand how to do all these questions, you will do well on the test. All right, so let's go ahead and jump into our first one. We are asked to find the limit as x goes to 2. Remember that this value always down here is an x value, right? This is an x. So it's basically asking what is the y as we approach 2 in the x direction. Well, if we trace our function up this way and trace it this way, remember that the two limits have to agree, the left and the right have to agree. They're both approaching the same y value of 4. Right? It doesn't matter the fact that the actual function value is 2. This would be discontinuous, right? It would be a removable discontinuity. However, the limit does exist because the left and the right match, and it does equal 4. So that would be C. Number 1. All right, number 2. Let's go ahead and look at that one. Graph of the function is shown above. For which of the following values of C, so C is an x, which x values does the limit equal 1? So basically, where is y equal to 1? Or at least the limit 1. Okay. So if we just work our way from left to right, y value of 1 is right here. So what you could even do is just draw a little line across here. So you can at least see all the places that it hits. You can even do a solid line of it. See all the places that it hits. So it definitely hits here, right? And then we just need to confirm that the limit is actually that value of 1 there. That is, right, because we approach from the left and the right. It is approaching the y value of 1. So that would be -2. It hits again here. We definitely approach that value from both directions, right? So that's at x equals 0. The third place it hits is over here. However, the limit does not exist there because it approaches from the left, but it does not approach from the right. So these two would be our answers, -2 and 0. All right, let's look at number 3. All right. The graph of the function is shown above. Which of the following statements is false? Which is false? All right, so let's just go through each one and see if we can determine if it's true or not. So the limit as x goes to 2 exists, right? Well, if we look at 2 is right here. Limit looks like it does exist. Yeah, it looks like it's 2, right? So limit equals 2. So yes, that's a check. That's good. The limit as x goes to 3 exists. Well, 3 is up here. It does look like we're approaching the same value from both directions. Going to 5, we're going to 5. So yep, it's 5. Check. Limit as x goes to 4 exists. Well, as we approach from either direction, 4 is right here. This looks like it's going to 2. This one, we're actually coming in up here, and it's equal to 4. So the left limit as x goes to 4 from the left equals 2. Limit as x goes to 4 from the right equals 4. So this limit does not exist. So this is a false statement. C. We could just double check by looking at the limit as x goes to 5. 5 is good. It looks like it'd be up 6 up there, push in both directions. All right, the next one, number 4. What values does the limit equal 0? So again, what x values, this is x, does y equal 0? So if we were to just go like that, it might be kind of helpful. And let's circle all the places where it intersects and see if the limit is actually that value. First one would be here. Well, our left limit is going to 0, but the right limit is actually going to -1. So this one is a no-go. The next place is here. Well, this one, it actually is on a completely different plane. This is the f of c value. However, the limit for 1 is actually down there at -1, so that's not going to work. So then we've got here at 2. That one's going to work because as we approach 2 from either direction, it is 0, so that works. So 2, and then 4 over here. The function is not defined there, but we are approaching the limit is good there from both directions. So 2 and 4 would be our 3 answers. So that would be choice B. Okay, next one up, number 5. What is the limit as x goes to 2 from the right? Remember, this plus sign means push it from the right side. Well, as we move from the right, we're going to be following up this curve here, and that is going up to 3. The right limit is 3. The overall limit would not exist, but the right value is 3. Right, number 6. Okay, so if you think back to the first way we actually solved limits, and that was by making a table, right? When we had this idea where, let's say we wanted to take the limit of some value here, well, we would take values that are really close to it. So if this was, say, 2, we want to find the limit as it goes to 2, then we would try 1.9, and then we would try 1.99, and then we would try 1.999, right? If you remember those. And then we would also go from the other direction. It would be 2.01, 2.001, 2.00. That idea. And we would find the y value, see what the y's are approaching. That's what's going on here. This is evaluating a limit by using a table. We're not given any information about what this function is, so you couldn't look at the graph or anything. We just have to be able to do it by looking at the table. All right, so which of the following conclusions is supported? First one, a limit as x goes to 3. Okay, so it looks like they all have that in common, limit as x goes to 3, which, as you can see here, 3 would sort of fit right in the middle there because we're approaching 3 from the left and we're approaching 3 from the right. You can kind of see what's happening here. And you can see by just looking at the chart, this is going to negative 8,000, in other words, negative infinity. This one's going to positive 8,000, positive infinity. So you can probably make some sort of conclusion here without even looking at your options. If the limits are going to infinity in opposite directions, well, then the limit doesn't exist. They're obviously not approaching some specific value. So that's going to be D. Okay, I'll take a number 7. All right, another table one, get a little practice on this, which is supported by the table. So again, if we were to look at the x values, what we're supposed to be approaching here, it looks like 2 sort of falls right in the middle here. So this is from the left, this is from the right. As we approach from the left, it looks like the limit is approaching -1, right? And as we approach from the right, it looks like the limit's approaching 6. So if we go limit as x goes to 2 from the left versus limit as x goes to 2 from the right, it'd be 6. So we can draw those two conclusions based on that. And then let's see what options they give us here. We got the overall limit of x goes to 2. Well, the overall limit doesn't exist, so that's a no. No here, because again, that's the overall limit. C, left is -1, right is 6. That looks good. The other one is just the reverse of that, I believe. Yeah, which would be incorrect. So your correct answer will be C. All right, number 8. All right, so we need to find the limit of a bunch of these functions put together. The thing to remember here is limits, you can actually sort of distribute them in. Basically, you can bring limits inside of these functions. So we're essentially going to look at this as the limit as x goes to 2 of h of x. And then times 5 times the limit as x goes to 2 of f of x plus limit as x goes to 2 of g of x. The only thing you really got to watch out for here in particular is your parentheses. All right, so let's go ahead and evaluate this. We're going to use this table up here. And we don't need any of, shouldn't need any of these values over here. Those are there just to kind of throw you off because we're finding the limit of this entire thing All right, so first of all, limit as goes to h of x would be 2. So it's going to be 2 times, and then 5, and then it should be, I'm going to put another set of parentheses here. And then 5 times limit as it goes to f of x, which would be 4, plus the g of x, which is negative 6. And then we just need to evaluate this. 2 times order of operations 20 minus 6. So 2 times 14, which is 28. You can just get tripped up in those parentheses there. So be very careful when you do that. Okay, number 9. Okay. We've got a limit here. So this one is an algebraic limit. You should not be using a calculator for this one. All the questions that you're supposed to be able to use a calculator have a little emblem up here, I believe. I'll make sure I point that out when we get to one. But this one you should be able to do without a calculator. On the AP test, you would not be given a calculator with this. How we would find this limit is, well, first of all, you try direct substitution. So you try to plug it in. Specifically plug it in the bottom, because that's all we really care about to know if it actually works first. We get 4 plus 2 is 6 minus 6, and we do get 0 on the bottom, which means the function is, we can't just say that the function is, the limit is non-existent. That's what we did on that one assignment. A lot of people just put, well, it doesn't exist because we get 0 on the bottom. That is not the case. We can't just stop there and be satisfied. So what we want to do is actually factor the bottom and the top and see if we can get some cancellations. So the top is going to factor into x plus 2 and x minus 2. The bottom is going to factor into x plus 3 and x minus 2. And you can see there we get our cancellation we're looking for. So now we can find the limit as x goes to 2 of this function, x plus 2 over x plus 3, and do our direct substitution. We get 4 on top and 5 on bottom, so that would be 4/5. All right, next up, we've got another limit here algebraically. Notice it does not show the calculator again. I don't know that the calculator even help you on this one, but we're supposed to find what is this the equivalent as. Immediately, you can see if you try to do a direct substitution here, you're going to get 0 on the bottom, so that's not going to work. So you have to think about, well, what do I do if I have radicals that I need to get rid of? And that is to rationalize, which is what we are going to do here. So when we rationalize, we multiply by the conjugate. In this case, we're going to do, you always have to do both the top and the bottom, because you can't just multiply one part of the fraction. That would change the value of it. But if you multiply the top and the bottom by the same thing, then it's just multiplying it by 1. So in this case, we're going to multiply this thing by square root of x plus square root of 2 over square root of x plus square root of 2. So it's the same thing as the denominator, except we change the sign, and that's going to do some good things for us. And let's see what we get here. I'm just going to leave the top as is for right now. We might need to end up distributing that. We'll just see what happens from there. But I'm just going to leave the top as is. So I'm just going to call it x squared minus 4 times the square root of x plus the square root of 2 over. Now on the bottom, when we FOIL this, square root of x times the square root of x is just x. The middle terms, if you remember, are going to cancel, but I'll go ahead and write them. It's plus 2 radical x, and then minus, that should be a radical 2. Radical 2, radical x. And then last one, minus radical 2 times plus radical 2 would just be minus 2. So what we end up with is x squared minus 4 times square root of x plus square root of 2 over, the middle terms cancel, x minus 2. All right, and now from here, we still haven't got quite what these answers look like, which that's the goal, is to make this thing look like our possible answer choices. So we need to obviously get rid of that denominator. The best way to do that is not to FOIL the top. That's just going to create some more messes. What we do want to do is actually factor that one right there. because if you're thinking ahead, think about what's going to happen. When you factor that, you're going to get a -2 when you factor it, because that factors into x plus 2 times x minus 2. And then we still got this times square root of x plus square root of 2 over x minus 2. And now we get the cancellation we're looking for. So we've got it factored out. Boom, those cancel. So then we're left with x plus 2 times square root of x plus square root of 2. And all the while, we still do have this limit hanging out here. We don't always write it, but it is still hanging out there. So let's see if this matches what we're looking for. And it does look like that is letter A. So we can be satisfied with that. All right, let's look at our next one, number 11. We've got two functions. All right, so this one is a bit tricky because it doesn't give you a lot of insight on exactly what you're supposed to do. Well, the thing is here, if you look at, if you think back to some of the theorems that we learned in this section, it doesn't explicitly say it here, but this is actually referring to something we call the squeeze theorem. The squeeze theorem. And it might be helpful. I guess it doesn't show the calculator up there. But what's going to be happening here is these are two functions that are sort of going to squeeze in the f function. It says that f of x is sort of squeezed in between these two functions, g of x and h of x. So the squeeze theorem says if a function is in between two functions, and I don't know what these functions look like, but let's say they some way look like this. So let's say g of x, that's a negative parabola. So let's say it's like this in some way. And then here's 1, right, as we're approaching 1. And then, so this is g of x. Again, I don't know exactly what this looks like, but just to illustrate the theorem here, there's g of x. H of x is a positive radical, so it's going to sort of go the opposite way. Maybe it looks something like this, right? And then you've got this f of x, which actually goes in between them. So f of x, I don't know, whatever it's doing. We don't even know what that function looks like, but it happens to go right through there. Maybe it's some sort of trig function. It sneaks right through there. And it just so happens that at this point 1, well, if it's greater than equal to both of them, then the limits of these two functions as they approach 1, if they're the same, so if the limit as g of x as x goes to 1 equals some value, we'll call that a, right? And the limit of f of x, which is up here, the limit of f of x, as x goes to 1, is that same value a. If those are the same, and we know f is either equal to or between them, well, then that means f has to have that same limit value of, so that should be h. F of x as x goes to a has to have the same value of whatever that a is. Because if those two have the same limit and f is between them, well, that means f also has to have that same limit. So hopefully that makes sense. How we're actually going to figure this out is determine if these limits are the same. So we need to find the limit of g of x as x goes to 1. Then we can just do a direct substitution. It looks like we're going to get -2 plus 4, which would be 2, plus 1, which would be 3. Okay. And the limit of h of x as x goes to 1, same deal. 1/2 minus 1, which would be -1/2, plus 11/2, so it would be 10/2, so that would actually be 5. Okay, so what happened here is the squeeze theorem actually fails here. We can't use it. In other words, can't be used. The reason why is because these don't actually equal the same value at this point, 1. So what's happening here is the h is actually up at 5. So this 1 actually maybe hits up here at 5. And then the g down here hits at 3. So they don't actually touch. So the f could be somewhere, anywhere in the middle here, and we don't know where actually it is. These two would have to be equal. If they were equal, let's say they were both 4, well, then we could say that the limit of f of x is 4 as well, because it's between them and they're the same. However, since these are not the same, we can actually not use the squeeze theorem. It doesn't do us any good on this particular case. All it tells us is it's the limit of f of x is somewhere between 3 and 5, but we have no idea where it is. We don't know if it's at 3.1. We don't know if it's at 4. We don't know if it's at 4.99. We have no idea where. We just know it's somewhere in there, but we can't say for sure where. So our answer is actually D. The limit cannot be confirmed based on the information given. Next question here. All right, so it looks like we've got a lot of stuff happening here. We've got 3 different ways of representing some sort of function. So we've got g of x as a piecewise function, we've got g of x as a table, and we got g of x as a graph. So we're supposed to figure out which of these could actually be the case. And all the information that it gives us about this g of x is that it is decreasing for x less than 0. That means it's sort of going down as we approach 0, like that. And it's actually decreasing for x greater than 0 as well. So that means it's sort of going down and down. We got 0 somewhere in the middle here. All right, it's actually decreasing in both directions. And the limit as we approach 0 is 3. So the y value there was 3. Okay. It doesn't say anything about the actual value. So maybe the actual value at 0 is up here at, I don't know, 7 or something. It doesn't tell us anything about that. But it does say that the limit is 3 and it's decreasing in both directions. So let's see if we can determine if that's the case. All right, so the limit as x goes to 0 must be 3. Let's plug in the first one here. See if this is going to work. Oh, sorry, I did actually one mistake on here when I was drawing this. I would draw it actually increasing. Decreasing would actually be going down like this. Sorry about that. For values greater than 0. My bad. Decreasing just meaning that the slope is negative. All right, so let's look at condition 1. So for values less than 0, we're going to plug it into here. So I basically have to plug in some values and make sure that they're going down as we get closer to 0. Basically, as we plug in bigger values, they're getting smaller. So we need some space here. So this is for 1. All right, so that means if I were to plug in, let's say, -2. Right? So g of -2. I would plug it into that top one. That's going to give me negative 4, 6 would be 10, over -2, and over -2. So that's going to be 5. And then if I were to plug in, let's say, g of -1, I should have a smaller value because it's supposed to be decreasing. All right, so g of -1, that would be -1 plus 3, which would be 4. 4 over -1, so that would be 4. All right, so that's going down so far. So that's on the left side of 0. As I come from the right, let's make sure it's still decreasing. So if I were to do g of +1, it should be still lower than that 4. So that would be -1 minus 3, which would be -2, -2 over 1. So that would become 2. All right, and then let's do one more to check g of 2. See if it's still decreasing. -4 minus 6 would be -2 on top, -2 over 2, which would become +1. So we're definitely decreasing because we're going 5 to 4 to 2 to 1. From either side, we're decreasing. So basically what we've determined, this function, -2, we're up at 5. -1, we're at 4. At +1, we're at 2. at 2, we're at 1. So this function is definitely decreasing from both directions, right? It's going down like that. It's decreasing. It's some sort of linear function, it looks like. It's not quite linear, but you get the idea there. So it is decreasing both directions. All right, the limit as x goes to 0 equaling 3. Let's check that out. So the limit as x goes to 0. We're going to use, both of them, we're going to use this one, right? And what we would need to do is plug in values as we approach 0. This one's a lot of work. Sorry, guys. So we're going to need to plug in like g of, let's say, 0.1. Sorry, let's start with the negative. Negative 0.1, g of negative 0.01, g of negative 0.001. So this is going to be approaching from the left. See what these values equal. And then as we approach from the right, g of positive 0.1, g of positive 0.01, and then g of positive 0.001. This is one of those questions on the AP test where if it's taking you this long at this point, it might be a good idea to just skip it and come back later if you have time. This is a pretty intense question. All right, so let's plug these in. What I would do probably at this point, if you can use your calculator, is just plug that top function into your y equals and then just make a table. And I'm going to, in fact, just take a second and do that. All right. And then we can just plug these values in. So negative 0.1. Table settings, right? All right, negative 0.1. Somehow I lost my function here. All right, got my function in. This one is 3.1. If I do negative 0.01, that gives me 3.01. Whoops. And if I do negative 0.001, that gives me 3.001. So I'm definitely approaching 3 from this direction. If I plug in 0.1, 2.9, 0.01, 2.99, and 0.001, gives me 2.99. So I'm definitely approaching 3 from the left and from the right. So we could definitely say the limit as we go to 0 is 3. All right, so all that to say, our first option there is a check mark because it is decreasing as we move along, and the limit is 3. All right, hopefully the next one doesn't take so long. Our second condition here, let's see if it's decreasing as we move along. So sort of as we move along the timeline here, the numbers should keep getting smaller. So we are okay here, negative 10, negative 100, negative 1,000, negative 10,000, getting smaller. But it actually then goes up to 10,000, 1,000. So it's okay actually because it's decreasing. We don't know what happens here, but then it jumps up and it's still decreasing again because it's decreasing from less than 0. At 0, it doesn't say anything about what actually has to happen at 0. So it's actually okay that it jumps up because it's allowed to jump up there. But then it starts decreasing again as we get past 0. So this is actually okay. It fits that first one. All right, now the second one, let's determine if the limit is 3. This is the one you might actually want to check first because you can see the limit is definitely not 3. This one's going to negative 10,000. This one's going to positive 10,000. So the limit in this one would equal DNE, does not exist. So we can throw that one out because the limit does not equal 3. All right, so let's check the last one. It is decreasing. Here, look, it's decreasing up to 0, and then it continues decreasing after that. So we're good there. Satisfies the first one. The second one, does the limit equal 3? Well, as you come in from this direction, it's going to 3. Coming from this one direction, it's going to 3 as well. It doesn't matter that the function value down here is not 3. We're not asked about continuity. So we're good. Yeah, this actually satisfies both of them. So 1 and 3 would satisfy this. So we want D. There's a lot of questions like this on the AP test where you have to like choose multiple, like multiple are correct. These are generally the harder ones. So good luck with those. Number 13, but that's why we're doing them on this test, so you have some exposure. These are all typical AP questions, which is why we're using the AP Classroom website as well. We mentioned that, but so you get practice solving these questions. All right, the graph of f is shown above. What are all values of x for which f has a removable discontinuity? All right, so removable, think about removable, you can just sort of fill it in. So I kind of just asked myself, can I fill it in with a single dot? Could I just fill in a little dot and then it would be continuous? So as I'm moving along here, move along this, oh, I got a hole, but I could just fill it in with the dot and then I can just keep going, right? So that one actually is right there at x equals 0. So that's a removable. The first one. Now when I get to this next one, I can fill it in, but I still got to jump up. I got to move my pencil down here. I got to jump. So that's actually not going to work there. Well, then I keep going on the curve here. Oh, I can fill this in, and then I can keep going on the same road. So x equals 2 would be another removable discontinuity. This one, this is actually just continuous, and then just starts going again some more. So it's continuous. It's not a discontinuity. Don't get confused there just because there's a dot there. It's just continuous at that point. So my two removable discontinuities are at 2 and 0, which would be choice C. Right, next question, number 14. I'm going to take actually a brief break here, and then I'll start on another video. That's a long time to listen to me do problems. So I'll pause here and we'll pick it up on the next video.